Hello. In this talk, I will present our attempts to try and reproduce temperature size rule using a life history optimization model. So temperature size rule means that at warmer temperatures, fish grows faster as juveniles, they mature earlier, but they end up smaller as adults. So all these three processes are important. And there have been many years and various attempts to try and explain this process mechanistically. So, which means if we can explain it mechanistically, we can also model it. Which means that to try and model temperature size rule, we need a model that would allow emergent maturation size at age, which are not as fixed parameters, but they actually come out of the model as a result. So we published a model like that in the American Naturalist in 2018 that allows emergent maturation size at age based on life history optimization processes, which means that the fish is eating, it's using some energy for metabolism, and the remaining energy is allocated between somatic pool and reversible pool that determines maturation and reproduction. And at the end of each year, if there is enough energy in the pool that is allocated for reproduction, the fish will reproduce. And also, depending on the mortality curves, there is an optimal life history strategy that emerges how quickly the energy gets allocated between somatic and reversible pool, and how much of that energy in the reversible pool gets allocated to reproduction, and how much actually is a reserve, as a fat reserve, which doesn't get used for reproduction. So now we want to add temperature into this model. And temperature speeds up life processes, basically. And there are two main aspects how temperature can speed up life processes. One is simply by increasing various rates. So basically, as temperature increases, we expect this kind of exponential increase in rates. And depending on the activation energy of the rate, that increase can be fast or it can be slower. And so here at the reference temperature, there is no change, but generally as temperature increases, we expect the rate will increase. But another key aspect of it is that this increase in temperature might be size dependent. So for example, now on the x-axis, we have mass, and this is metabolic rate, and this is change in two temperatures, for example. So the rate might just increase evenly across all sizes, as shown in this solid line, or it might increase more or less in bigger individuals, which is determined by this coefficient C, whether it's positive or negative. So this is actually what we have introduced in the model. We allowed metabolism intake and size-dependent mortality, which is like a natural predation mortality, to scale depending on temperature, and also to scale depending on body size. So we're allowing this temperature-body size interaction of scaling. We looked at 42 different scenarios and parameter combinations, which is a lot of them. You can actually read this later. And with 42 parameter combinations, we got 42 scenarios and 42 emergent growth and maturation curves. Here they are. So basically, we want to see that juveniles are growing faster, that fish are maturing earlier, and that adults are smaller. So how many of these 42 scenarios produce these kind of results? Basically, we found that there are two main ways how temperature size rule can emerge. Mainly, metabolism has to increase with body size faster than intake. So as both of them are increased, but metabolism increases faster, and intake actually increases less in large individuals. So we get this big gap in size between in the energy budget. It is also possible that either of them decrease with body size, metabolism, and intake, but still the difference with bigger body size has to be increasing. So there is a bigger net difference between these two processes. But it is also possible that metabolism doesn't have to increase at all, And actually, Henry Wooten recently published a paper in 2022 in Ecology Letters showing that temperature size rule can emerge without any difference in base-like metabolic rate. And we can actually reproduce it, again, as long as there is a negative sort of net effect of intake and metabolism. So intake has to increase initially and then decrease. But in each case, life history optimization was essential, because without it, we basically cannot, with physiological processes, we cannot reproduce emergent life history. So the way how the energy is allocated between somatic and reversible energy pool actually is very important. And the result, the take-home message, is that temperature size rule is likely to be a combination of physiological processes related to food or oxygen intake and use, and life history optimization, which is the energy allocation between growth and reproduction. So to understand how it works, we need a cross-disciplinary research and dialogue. And this paper is accepted in the Biological Bulletin special issue, An Oxygen Perspective on Climate Change. And you can actually play with this model yourself. If you go to this GitHub account, you can download an Excel file that allows you to play with various parameters and see what kind of growth you will get. So with this, thank you. And we thank our funding body, European Union funds, and see you at the conference.